Alrighty.
Mr. Wood?
Yes.
Like, the optimization format that we're turning in is the one that was in our notes that was like...
Yes, the very last page of the notes. The very last page. All right, so while you're getting that collected, if you want to also turn in our notes to our 5.2 section here, we're going to go through this idea. So we're going to kind of introduce we're going to kind of make a little bit of a weird turn here in our calculus adventure. All right, and that is we're going to start talking about something what we're going to call area under a curve. Okay? And when we say area under a curve, we really mean like the area. So let's say we've got a function like f. Okay. Let's say we've got a function f from like a to b here. Okay. To talk about the area under the curve, we really mean the area between the curve and the x-axis. Okay. We really mean the area between the curve and the x-axis. Okay, because obviously we just talk about the area under the curve, it's going to go on for forever if we just go completely underneath it there. And so this is what our ultimate goal is, to be able to kind of like find that quantity. Okay, and we'll start off with some very basic curves. Okay, so in our very first graph here, you can see we have a function. It might not be so clear what it's supposed to be, but it is this curve right here. Okay, which I believe is at 3 there if I read my 0.51, 1.52, 2.53. Yep, okay, just like that. Okay, and we want the area under the curve from 0 to 4. Okay, and again, it's maybe hard to read here, but I believe this is 0 right here. Okay, and then let's see, there's 1, 2, 3, and then 4 goes to the very end there. I'll get you. Okay, right there. Right. And we're trying to find this area right here. Okay. 0 to 4 there. And so what is the area underneath this curve from 0 to 4? You can count your squares if you want to, or we can just do what? 4 times 3, or 3 times 4, or whatever you want to say there. It's going to be 12, right? We don't really have units here. You could say, I guess, what you could say, you know, square units if you wanted to, or something like that. There's no units. It's kind of weird to, you know, come up with some, but we'll just say, you can say unit squared if you want to. Okay. All right, very good. Let's try the next one here. So next one, we had a horizontal line. That was our function. Now we have a diagonal line here for our function f. And then we want to only go from 1 to 3. So now we want to be a little more careful. Again, here's our curve. Okay, like that. We only want to go from 1 to 3. So here's 1 right there. And then here's 3 right here. And so that means we want to find the area of this region. Again, it's the area under the curve, but also between the curve and the x-axis. Is really more an accurate statement there. Between the curve and the x-axis. Okay. What kind of shape do we have here? It's a trapezoid, okay? So if you remember, the area formula for a trapezoid is 1/2 base 1 plus base 2 times the height, or base 1 plus base 2 over 2 times the height, or you know, depending on how you kind of like formulate it there. Okay. The bases for our trapezoid, okay, the bases, we don't want to think about top and bottom, all right, for bases. We want to think the bases are the parallel sides. Remember, a trapezoid by definition has one pair of parallel sides, or I guess depending on where you are, it could also be at least one, but anyway. All right, so what are our two bases here? What are the lengths of our two bases here? 2, right? And 4, okay? And so we'll do a 1/2 times 2 plus 4. And then what is the height of our trapezoid? We go from 1 to 3, so the height is 2. Okay, the height is 2. Okay, again, be careful when we establish this right here, which is a length of 2, and this right here, which is a length of 4. When we establish those are our bases, the height must be perpendicular to the bases, and so that creates this. This is the height right here. Okay, that's the height of our trapezoid. Thank you. All right, so good, there's that. Which, oh, sorry, I guess I should finish calculating this. So 2 and 4 is 6. Half of that is 3 times 2 gives us 6. Again, units squared there. All right. All right, next. Area under this curve. So again, you can see this curve right here. What kind of shape do we have here? A semicircle. And we're going from 0 to 6, so there's 0 right there, there's 6 right there. And so we want, again, the area under this curve, but above the x-axis. Like that. Area formula for a semicircle, 1/2 pi r squared. Okay. What is the radius of the semicircle? 3. Very good. Yeah, 6 is the diameter, right? 6 is the diameter, so half of that, 3. Okay, so it's 1/2 pi 3 squared, which is 9/2 pi unit squared there. Maybe we can leave the pi out. Don't have to multiply it through. Okay. Easy peasy. All right, here we got another curve. Interesting here. Again, the curve is this piece. Ugh. Okay, we go from negative 0.5, so that's right here, negative 0.5, to 4.5, which is right, there. So again, we'll try and find the area of this region here. Okay, so what kind of shape do we have here? A triangle. What is the area formula for a triangle? 1/2 base times height. Okay. What is the base length of this triangle? I hear 4 and 5. 5. Okay. Oops, I'm going to put it up here. So 1/2 times 5. What's the height of this triangle? It is also 5. Yeah, if you look here at the very peak, right, so our base of our triangle starts at 0, and the very peak goes up to what that blurred image I'm just going to read as 5 there, all right? And so it's, 25 halves then. Units squared for our area there. And then finally we get to this curve. All right, and we want to find the area under the curve from 1. So here's again 1 to 5 right there. And so we'll kind of draw some boundary lines here for ourselves and then kind of. Okay, and so what is the area? What kind of shape is this? Yeah. So we don't really have a nice geometric shape that we can use here to kind of like fit this thing. But what we can do is kind of like, well, we can estimate the area, can't we? Because like here's from like 1 to 2. So like for example, this little block right here, right? What's the area of that little block? 1. It's 1, right? Because it's like 1 by 1, so that's got an area of 1. And so we could do it another one right here and another one right here. So 2, 3, and let's just try and fit in full blocks for right now here. This is something you guys did maybe way back in like elementary school, I feel like. So there's a 5th one. Yeah, bless you. There's a 6th one right there. But of course, then we have these other like not quite full blocks here. But what do we maybe want to say? I mean, can we make some more here? I mean, it looks like right here we can maybe like make another one, right? By adding on like a little piece right here to here, and then make that maybe 7, and then we can make like this one, like an 8th one if we like add on this piece, maybe some of this piece too to it. So like maybe it looks like we get about 8, you know, really total there. You know, maybe it looks like we get about 8. Okay, maybe. And so when we come across problems like this, for now, okay, we are going to approximate. We're going to be trying to approximate area under the curve for a situation like this. Eventually, we'll get to the point where we can find the exact area under this curve. But for right now, for today, we're focused on methods of approximating areas under curves when necessary, right? Obviously, here, not necessary. We can find the exact area. For the previous examples, right, all those, we could find the exact areas. But for situations like this, right, we need to be able to, we want to at least try and approximate it for right now. All right, so turn the page. All right. So we're going to start with another curve here. All right, we're going to be given the function y equals 25 minus x squared. So you can see there is our curve, okay? So it's like, you know, part of a parabola, I guess, there. Okay. And we're going to find the area from 0 to 4. Okay, so we're going to focus on the region between 0 and 4. So we're going to start, like, draw my boundary lines here. The 0 is the other axis, okay? And so method 1, the first method we're going to kind of examine here is we're going to divide this region into 4 rectangles, okay, where the left end point of each rectangle comes just under the curve, and then find the area. All right, so what do I mean by that? So 4 rectangles. So if we're going, okay, if we have to go cover from 0 to 4, so if going over the interval from 0 to 4, okay, using 4 rectangles. Okay, and we're going to use rectangles of equal width here too. That wasn't specified in the directions, but we're going to be using rectangles of equal width here too. So each rectangle, well, what will be the width of the rectangle? If we have to go from 0 to 4 in 4 rectangles, what will be the width of each rectangle then? It's got to be 1, right? So yeah, each rectangle will be 4 minus 0 over 4 units wide, or 1 unit wide. Okay? So we'll kind of break it up here. So here's our first rectangle right there. We'll call this like it's going to be, well, actually, so from 0 to 1, and then from 1 to 2, we'll create another rectangle. 2 to 3, and then 3 to 4. And that's going to create, you know, 1, 2, 3, 4 rectangles there. Okay. And so we're going to draw these, and it's not necessarily an easy, like, so where the left end point of each rectangle comes just under the curve and find the area. So in other words, this first rectangle here, we're going to judge the height of this rectangle using the left end point. So even though this rectangle goes from 0 to 1, we're going to use the left end point of the interval to judge the height of the rectangle. So we're going to go like all the way up to here, and then draw, you know, horizontally across, and then down. Okay, and we'll call this R sub 1 for rectangle 1 there. Okay. Our next rectangle, will it be taller, shorter, or the same than rectangle 1? Shorter, right, because if we use, again, for rectangle 2, we're going to again use our left endpoint. So just like we did for rectangle 1, we use our left endpoint, which is 0. Now we're shifting our point of reference here. We're using rectangle 2. Our left endpoint here is at 1. So we're going to use the height of the rectangle, or the curve, sorry, at 1, and then draw across like that. Okay, and that creates rectangle 2. And so on and so forth, right? So for then this third interval here, we're going to use the left endpoint, which is 2, for its height. So going up to right here on the curve, going across our interval length and then on down. Okay, R3. And then the last one, our fourth interval here, it goes from 3 to 4. Again, we're using the left endpoint to determine the height, so we'll go up to the curve there and across and on down. And there is R4. Okay? Questions on any of that? So there's our subdivision there. All right? And so what we're going to do then is approximate the area. Okay, so we're finding the area, but we're really approximating the area here by finding the area of the individual rectangles. Whoops. Okay? So the width of the rectangles will all be the same, right? What are the width of all the rectangles going to be? 1, right? So we can always put a 1, 1, 1, 1 in there. Okay? Times, of course, now we want to multiply by the height. Or the length, depending on what you want to say. I'm going to call it the height just because it makes more sense, I guess, in this context. But the width of the length. Width times the length. Length times width, height times width, whatever you want to say there. Okay? So for this first rectangle, what's the height of this first rectangle? Yeah, it looks like it goes up to 25, right? And in fact, it is. Okay, so that's easy. So the area of that rectangle is 25. Again, units squared if you want to. I'm just going to put 25 right now. What's the height of the second rectangle, though? $22.75. Okay, because it looks like it's maybe about halfway between the 22.5 and the. What is that? 22.5. But well, okay. So I don't know if that'd be 22.75. So what is the exact height here? 23. 24. Well, so what is determining the height of these rectangles? What did we use to determine the height of the rectangles? It's the curve here, right? Okay, so we use the left endpoint of this interval, which is at 1, and we use the curve to determine how high up we went. Well, what is the value of the curve at 1? It's 24. So it's going to be f of 1, which is equal to, 24. Okay, so the area here of this thing will be 24. Okay. Okay, what about the third rectangle here? It's the value of the curve at what? At 2 now, right? We're going to use the left endpoint of this interval, so f of 2 gives you the height there. And what is f of 2? 21. Okay. And then r of 4. Okay, well, the rectangle 4, not r of 4. The rectangle, the fourth rectangle here, we're going to use the left endpoint 3. Okay, so 25 minus 3 squared. Well, I'm going to do f of 3. I'll write that first. So f of 3, which is then equal to 16, Okay. Okay. And 25, we could say that's the same thing as f of 0 there. So we used f of 0, the left endpoint. We used 0, the left endpoint of the first interval. We used 1 then for the next rectangle, the left endpoint. Okay. 2 is the left endpoint of the third interval there for our third rectangle. And then for the fourth rectangle, our fourth interval here, we use 3 as the left endpoint. Notice 4, right? We never used 4, right? We didn't use 4 because it is not the left endpoint. It is not the left endpoint of any of our intervals that we have here. Okay, we're only going from 0 to 4. 4 ends up being a right endpoint. We're not going to use that in this case. All right, and then what are we supposed to do with these areas now? Add them up. Okay, so we'll add them up. We get 16 there, and then 2, 2, 2, 8. Okay. So 86 is what we get. Okay, and again, we'll say square units. Okay, 86 square units there. Okay, so again, I'm going to say here, we did not use, f of 4 because x equals 4 is not a left endpoint of an interval. Okay, So in other words, sometimes we're going to skip, x values that are in our interval there because it depends on what kind of endpoint we're using here. Okay, we're using the left endpoints here specifically, so we're going to miss using that for the endpoint there. Okay, because we're not going beyond the 4. We're only going from 0 to 4, so we stop there. All right. Well, do we expect this sum here to be an over approximation or an under approximation? Over. Okay, what kind of gives it away here? All the rectangles, right? All the rectangles are going over and above the curve there. Okay, and so we're adding on this extra space. Okay. Over approximation. Okay, so we are over approximating here. Okay, or over approximation, I shouldn't say. Over approximation. All right, questions on any of that? All right, let's try another one here. It's the same curve, so it's y equals 25 minus x squared. Okay, we're still going to go from 0 to 4. Okay, and we'll do 4 rectangles again. Okay, I guess they'd always written the directions there. Okay, but now we're going to use the right endpoints of the intervals. So we're still going to go from 0 to 4. So there's 4, there's 0. Okay, we're breaking up into 4 equal intervals. So what's the width of each interval going to be? 4. Okay, well, not 4. It's going to be 4 is the full width. And if we're breaking up into 4 subintervals, what's the width of each subinterval going to be? Sorry, just 1, right? Sorry about that. Maybe I wasn't very clear about how I described that. Okay. So again, subinterval width will be 4 minus 0 over 4. Okay. So now we're going to use the right endpoints. And so our first interval here is from 0 to 1. Our first subinterval is from 0 to 1. We're going to use 1 now to determine our height. So we'll go up from 1. Okay. And right here, that determines our first rectangle. Okay. So you see we're going now under the curve somewhat, right? That first rectangle from 0 to 1, we're going to use 1 for the height, and then draw a little rectangle there. So this is our sub 1 again, still. Okay. 1 to 2, all right, again, 2 is our right endpoint, so we're going to use 2 to determine the height of our rectangle, f of 2 to determine the height of our rectangle there. Something like that. And then 3, same deal. We're going to go up from 2 to 3, so 3 is our right endpoint. And then from 3 to 4, our last interval here, 4 is our right endpoint, and so we'll go from there to there. So R2, R3, R4. Okay, just like that. Again, approximating the area underneath this curve from 0 to 4. Okay, so again, we will find the areas of these 3 rectangles. Okay, all of their widths, again, will be 1, so that's easy enough. And then we'll just multiply by their heights. Okay, so for the height of this first rectangle, we're going to say the height of that first rectangle is f of what? F of 1. We're using the right endpoint there. Okay, the second rectangle, it'll be f of 2, right? We use 2 for that second rectangle. And then for the third rectangle here, f of what? 3. Again, our right endpoint. And the final rectangle, whoops, f of 4. So here we do use 4. Here we do use the 4. But now what point aren't we using? We aren't using the 0, right? Okay, so the 0, that left endpoint gets ignored. We're using the right endpoint 1, right endpoint 2, right endpoint 3, right endpoint 4 there. Okay, and so we can then go ahead and find these calculations too. Okay, so let's see here. We said, in fact, we have the earlier calculations already, right? We have f of 1, we have f of 2, f of 3, so 24, 21, 16. Okay, and then the last one, which is f of 4, 4 squared is 16, 25 minus 16 equals 9. Okay, and again, we add those up. Okay, so we get 20 there. 2, 4, 6, 7, 70. Okay, for our sum, units squared. Okay, do we expect this to be an over approximation or an under approximation? under right. Okay, so, and again, we can kind of like, point here. Oops. Missing area. Okay, so it's missing those areas there, right? We're missing those little pieces. All right, this piece right here is not accounted for. This piece, and this piece, those pieces are not accounted for. All right, so yep, under approximation. All right. Questions on any of that? So far, so good. All right, next one here then, we're going to do one more. One more here. We're going to still divide. So same situation, same curve, okay? So it's still y equals 25 minus x squared. And it's still from 0 to 4. Okay. We're still going to divide the region into 4 rectangles. So it'll still be, 0 to 4 here. Going from there to there. Okay. 1, 2, 3. So it's still going to be, 4 rectangles with width of 1. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 rectangles there. But now we're going to use the midpoint of these intervals to find the height. So in other words, for our first interval here from 0 to 1, what's the midpoint from 0 to 1? 0.5. We're going to use the height at 0.5. So here's the height at 0.5. We'll draw our little rectangles here. From 1 to 2, again, what's the midpoint of that interval? 1.5. So we'll use the height at 1.5. So you're going to go up from 1.5 to like right there. Okay, and go from there. Now, actually, I'll finish and then I'll ask my question. All right, 2 to 3, midpoint is 2.5. So we'll go from 2.5 up to the curve right here. And then from 3 to 4, the midpoint is 3.5. So like roughly right there. Okay. What is the benefit of using this method right here? What's the improvement here? You have Matthias?
So you're kind of overestimating on the right half of the rectangle and underestimating on the left half of the rectangle. So it's supposed to sort of balance out, I guess.
Yeah, exactly right. We kind of like eliminate that, not eliminate, sorry. There's still going to be some error there in our approximation. But we at least are able to better account for the fact that we're going to have over approximation, under approximation. We kind of like Matthias said, kind of balance it out. Okay, in this case, right, on the right part of our first subinterval here, we have an over approximation, but on the left part, we also have an under approximation. It's more clear maybe like right here where we have, again, under approximation for this part of R3, the left part, but the right part we're over approximating. So ideally those will help to balance out and not be such like gross over approximations or gross under approximations. So why don't you guys go ahead, come up with the area there of this particular region, or sorry, using this region using this method. Okay, and I will do the same. Remember what we use to determine the height of the rectangles, okay? And also remember what the widths of the rectangles still are, right? Okay.
Give up so soon. Simple math, right? Yeah. He is.
All right, so hopefully you got 79 square units there. All right. Our heights, right, are f of 0.5 now, because even though the width is 1, right, 0 to 1 is the width of the subinterval, we're using the value of the function at the midpoint of that interval, which is 0.5, okay, to give us this area, right, to give us the height of the rectangle, Same thing here. 1 to 2 is the width of the subinterval, so the width is 1, okay, but then what did we use to get the height? It was f of 1.5, okay, the midpoint there, so on and so forth, then 2.5, 3.5, so on. And so you get about 79 square units there. Okay, do we expect this to be an over approximation or an under approximation based on this?
Or.
What's that?
Or.
Or. Ah, the answer is or. No, there is an answer to this. Okay. So over is what I hear. Anyone want to try and defend it? Okay, it is an over approximation. Just make sure I've got that here right, but I'm pretty sure. Yeah. Okay. It is an over approximation. Okay. And this one I will give to you. It has to do with the concavity. Okay, so for over approximations, concave down. Okay, and under approximations, concave, well, you can guess there's going to be concave up. Okay, for those kind of, for the midpoint stuff. It has to do with concavity. Okay, concave down, concave up. All right, so yes, question. What is the point of inflection? Great question. So that in those cases, I don't think that you would be asked then what it would be an over or under, or it'll be more like obvious, I guess, like in that case kind of thing. But as like the general behavior rule. But I see what you're saying. Yes, if it changes, right, we're gonna run into some issues, right? But it will be possible to figure it out in other scenarios. So I can't come up with like a a random question. We'll have to kind of cross that bridge when we get there. All right. So anyway, so what I'd like you guys to do is go ahead and try. Okay. Well, actually, I'll help you set up the next one here, and then we'll maybe have you try the rest. Okay. The next two. Okay. On your own there. So new curve. Woo. All right. So suppose you have to find the area under the curve y equals 3 or x cubed plus 1 from 1.5 to 3. Okay, so we're going from 1.5, which is right here, okay, to 3, which is right here. Okay, and we want to do that with 6 rectangles. 6 rectangles here. Okay, so we got to figure out our width for our new subintervals here. You can kind of see it in the picture what it's going to be because, well, you can see 6 nice little rectangles that fit there between 1.5 and 3. But let's do the calculation here too. Okay, so the subinterval. Okay, well, what's the total distance that we have to kind of traverse? From 1.5 to 3, what's that total length of that interval? 1.5, right? Or which you can get by doing 3 minus 1.5 there. And what we want to divide that total distance up into how many total subintervals? 6. So we'll take that total length and divide it by 6 into 6 equal subintervals. And so we get, yes, 1.5 divided by 6, which if you can't tell from right down there, it does give us 0.25 for each subinterval there. Okay? So in other words, there's 1, 2, 3, 4, 5. Okay? Now, one thing I wanted to point out here that I didn't earlier, right? When you have, for example, in this situation, right, we have 4 calculations. We have 4 different values we want to find of the same function. I don't know if you guys have seen this before. I feel like I've shown at least my pre-calc class, and I'm sure other teachers have shown theirs, but just in case you haven't. So in this case, right, we're going to be evaluating the function 25 minus x squared several times. And so what's helpful is if you type that 25 minus x squared into your y1, if you press second graph, that gets you to your table. Now, my table looks like this because I have set a particular option, okay? If you press second window to table setup, all right, you can change the independent variable, which is normally on automatic, because that means your calculator will automatically fill in what the independent variable is, probably starting at 1 and counting up by ones kind of thing. You can have it ask you. So if you highlight that, hit ask, now when you go to your table, you can type in whatever value you want. So here when I did 0.5, okay, I got the 24.75, or 1.5. I got the 22.75, or the 2.5. I got the 18.75, and the 3.5, so on and so forth, the 12.75. So you can use the same thing here if you like. Okay, for this, of course, you want to be careful with your setups now. Okay, so I'm going to, let's see here. We're doing the left endpoint rectangle first, so it's going to look like this, and then this, and then this, and then this. This, and bless you, and then this. Okay, so R1, R2, R3, R4, R5, R6. So I'll go ahead and do the area for R1 here first to help you out. Okay, what is the width of this first rectangle for R1? It is 0.25, and then times f of, well, we're using our left endpoint here, so we're going to use 1.5, so f of 1.5. Okay, so be careful here. What I'd recommend you maybe do is you can actually type in 0.25 times, and then what your function is. Your function is going to be x to the third plus 1. Okay, so I've typed into my y equals 0.25, the width of the sum interval, times the function there. And so now when I type in my values, that gives me the actual area there. So, I guess we'll say 1.094. Okay, like that, and so on and so forth. So you guys go ahead and come up with the rest of those rectangles there, all right? And I will do that too. And if you get done the method 1, you want to move on to method 2 and try the right endpoint, and then go ahead and move on to method 3 there and get the midpoint for this one. Bless you. Please don't forget to also identify whether your approximation is going to be an over approximation or an under approximation at the very bottom of those questions too. You can use your picture to help you. So here's the left endpoint sum right there for you. Okay, again, left endpoint, method 1. Okay. Yes.
For these, how far are we allowed to be off on the total area because of rounding?
Well, so did you round to 3 decimal places
Yes.
for your situation? Okay, so how far off were you from mine then?
Well, I didn't like round, I truncated it. So
Okay.
I was off by.
So as long as you're consistent, then I would say I think you should be okay.
Yeah.
So, yeah. That is fine.
I don't know.
Bless you. Okay, and then here is the right endpoint approximation. Right endpoint. By the way, these things sometimes are abbreviated REA, right endpoint approximation. Of course, left endpoint would be LEA for left endpoint approximation. So REA and LEA. But there's that. I'll leave that up there. And the other one's just called midpoint. Okay.
I think you're a good guy. Yeah, you have all of those. Do you have all of those? You're the right way.
What was it?
I forgot to multiply to this point.
Does that kind of seem bad?
That's right.
Kind of seems bad.
Okay. Question? Sorry. Okay. I'm going to walk over here and listen to Emma talk to me. But she doesn't have a question. The midpoint. How do you find the midpoint? That's the distance of the circle. Midpoint between those 2 points. Subtract and divide. Well, I mean, yeah, it's average. Add up, divide. It is. Yes. Now, if the distance from here to here is 0.25, and the distance from this midpoint to this midpoint is also going to be. Convenience though, rather than like adding up divided by 2, you just take this one and add 0.25 and you get your other midpoints. So that's your next midpoint. If you don't believe me, you can add the 2 up, divide by 2. It's a point. 2 plus 1. Yeah, that's what it is.
You what you know.
You can just add 0.25 to all those things. You get it. Okay. So the homework is the next page there. So if you want to get into the homework, feel free, to start on that next page. You're feeling good, okay? If it doesn't ask you to, then you don't need to. Especially for stories like this where it's both like as well. Just kind of guess. It's harder when you're mixing up behaviors here. So yeah, I wouldn't worry about it if it didn't ask you. Yeah. So Emily. Okay, so. Okay, I think I see why.
This worksheet, the one that you just did.
I said it wouldn't really.
Oh, yeah, like how we back what you thought. Alright, this is the end of where something.
Okay, I'm going to go ahead and post the final one here, but I do have one other thing I want to talk about. I do have one other thing I want to talk about here too. Okay, so when it comes to the midpoint, I kind of like gave to you guys how to tell whether it's an over approximation or under approximation, right? For midpoint, we can say under approximation if the graph is concave up for the whole interval, and over approximation if the graph is concave down for the whole interval. Okay, so concave up is under approximation, concave down is an over approximation. All right. So we never really talked though about how to determine with the right endpoint or left endpoint, whether they are over or under approximations. Now, of course, we can look at it and see clearly, Mr. Whitmire, this is an over approximation, right? And we had another over approximation, so let's kind of like see our graph here. What's happening here in our graph? This is an over approximation. And then here is the other, well, sorry, let me do it this way maybe. Sorry. So right endpoint, in this case, we said was an over approximation. Okay, so we can see what's happening on our graph. So the right endpoint here, over approximation. But then for the previous right endpoint that we did, which is right here, the right endpoint was an under approximation. What is the difference between these two graphs? What's that? So this graph is decreasing, and it ends up in our right endpoint being an under approximation, whereas this graph is what? Increasing, and it ends up in our right endpoint approximation being an over approximation. Okay? Whereas if we go to our left endpoints, right? Left endpoint, here our function is increasing, right? And the left endpoint is an under approximation. Whereas here, our left endpoint was an over approximation because our function was decreasing. Okay? So, over approximations for left endpoint and right endpoint have to do with whether your function is increasing or decreasing. Okay? It kind of just makes sense. If your function's increasing, that means your left endpoint will always be smaller than your right endpoint. Okay? So your function's increasing. Okay? If f is increasing, you know, all your little intervals here, the left endpoint will be lower than the right endpoint. So the left endpoint, since it's lower, will be under. Okay? And then the right endpoint will be over approximation. But if f is decreasing, actually I should use a different color here. Christmas colors. Okay, if f is decreasing, then it will be reversed. Okay. And of course, for the midpoint is the concavity. Concave up, under approximation, concave down, over approximation. Okay? So something to keep in mind, because this is a kind of question that we can be asked there too. Okay. The good news is you can always draw a little sketch for yourself like this and kind of convince yourself, you know, okay, I'll draw a little f increasing function, and then approximate the left endpoint approximation, or do the right endpoint approximation, and figure it out that way too. So you can also kind of convince yourself one way or the other too. It doesn't necessarily require that you just have that known,